Thank you. Yeah, we are going to talk about Rowhammer attacks and first about ourselves. My name is Daniel Gruss. I'm currently a postdoc at Graz University of Technology, and you can reach me via Twitter or email.
My name is Moritz Lipp. I'm a PhD student at the same institute in the same office. You can also reach me on Twitter, write me an email, or come to talk to us later on. We also will be at DEF CON.
And my name is Schwarz. I'm also a PhD student, same office, same university, also on Twitter, and you can also drop me an email, talk to us. We're here the rest of the conference. Of course, it's not just only us three. There's a whole research team that did a lot of the work here, what we are going to present, consisting of Clementine Maurice, Daniel Genkin, Jonas Jofinger, Lukas Raab, Lukas Lamster, Misika Dadese Aga, Sioli O'Connelly, Wolfgang Schöchli, and Yuval Yarom. Okay, let's start directly into the topic. We are talking about Rowhammer today. It's a fault in DRAM modules. So we have to talk about DRAM first. And you might all know that. You have it on your servers, your computers, your laptops, this DIMM, your memory. And most of you will have more than one of that, like 2 DIMMs in your computer. They're connected to your CPU via different channels. And they also usually have 2 sides, so a front side and a back side, and we call them ranks. And if we zoom into that a bit more, we have a lot of chips on those DIMMs on both sides. And those chips then consist of multiple banks. And in these banks, we can find some rows, a lot of rows, and also a row buffer. We'll talk about the row buffer in more detail later because it's a really important part for row hammering. Right now, we're focusing on the rows. And on the rows, such a row consists of multiple cells. The cells are the actual bits that are stored in memory. Every cell represents 1 bit, and it consists of 1 capacitor and 1 transistor. And this is where the data is actually stored by either charging the capacitor or having it not charged.
Okay, this sounds all very complicated. Maybe we start with a simple case where the CPU wants to access 1 row. What happens then?
So if you want to access data, we can't do that bytewise in the DRAM. We always have to access 1 row. And we have to read 1 row. So first of all, we have to activate the row we want to read, where the data is stored that we want to retrieve. And so the memory row is activated there. Then it's copied into the row buffer. So the whole row is copied into this buffer. And only the contents of the buffer can be actually read by the CPU and is returned to the CPU.
Okay, that sounds really slow, actually. And what happens if the CPU now wants to access another row?
Then we do the same thing again. So we want to access a different row. We have to, again, activate that row first. Then we have something different in the row buffer. We have to overwrite the row buffer with the new row. If we change that content before, we even have to write back the row buffer to the old row before that. Then we have this new row in the row buffer, and we can return this value to the CPU. So this is quite slow, as you have said.
So it's always slow. Is there a case that is fast? For instance, if we access the same row again?
Then we don't have a conflict. So that's a lot better for performance. And if we want to access data that's in the same row, then this row is already in the row buffer, and we don't have to copy anything, and we can directly return the content of the row buffer to the CPU. So this is fast. This is a row hit. We hit the same row again, and this is actually pretty fast.
So what you're saying, basically, the row buffer is a cache where you can store 1 row and cache it. And if you now have access to a high resolution timer, what you can do, you can actually time how long it takes to load the address, and we can distinguish the cases where we have a row hit and a row conflict, as we can see on this plot. So we can easily find the threshold in between, which allows us to distinguish between row hits and row conflicts.
Yes. And as Michael said before, these cells consist of capacitors, and capacitors discharge over time. If they discharge over time, we have to refresh them frequently. And this is also what happens in DRAM all the time. But
so if we want to read this row and we copy it to the row buffer, we actually destroy the content of the row because we discharge all the capacitors to measure them. And
are there also other effects?
Yeah, that's a problem there because everything is so small in there already that we also discharge neighboring capacitors there. And that's a bit of a problem, right?
And if we do that often enough?
If we do that often enough and the contents are not refreshed fast enough, then suddenly we have bit flips and we get different content in neighboring rows that we can't even access. Okay,
this sounds quite bad. But let's see how widespread this issue actually is. Maybe this only affects something like below average, substandard DRAM modules that fell off the truck somewhere or something, I don't know. Let's talk about DDR3 and DDR4 here. Of course, it also affects DDR2. We also saw bit flips on LPDDR2 modules.
No one uses that anymore.
Yes, that's too old. But for DDR3, there's a study that showed, from 2014, Kim et al. Showed that 85% of the modules they had were affected. And later on, 2015, Seaborn and Julian showed that 52% of the modules they had were affected to their specific hammering method that they used in software. For DDR4, people first believed, yeah, this is safe. You can't flip bits there because that's also what the vendors claimed. But we tried it and it works. We showed bit flips on DDR4 in 2016. Also, there was a paper that had a small prevalence study with 12 modules and there 8 modules were affected. Kim et al. In their original paper also had a correlation to the manufacturing date of the module. So they showed that this seems to be correlated with the manufacturing date. So, yeah, bit flips everywhere. What do we need to induce Rowhammer bit flips? We want to reach the DRAM, so we need to have uncached memory accesses. We need to bypass the cache somehow. This also has to be fast. And this is a problem because uncached memory accesses are much slower than cached accesses. And now we want to be fast so that we are faster than the next row refresh. And we also need to target the accesses. So we need to access the correct rows that trigger such bit flips.
So the question arises, how do we get enough uncached accesses? Because we have the CPU cache, and whenever we load some data, it's stored in the cache. And it remains in the cache for subsequent accesses, so that those accesses are pretty fast, and makes our systems very fast that we have them nowadays. So we have different methods that we can use to remove data from the cache, so that the next access will be loaded from the main memory. And the first thing is the CLFlush instruction. And this instruction was also proposed in the original paper, and it's an unprivileged instruction that you can use to just remove the address from the cache.
In 2015, we then showed that we can also do this with cache eviction, even from JavaScript. You might remember the name Rowhammer.js.
Because, of course, at some point, the cache is too small, and whenever we load more and more data, at some point, the CPU needs to decide what it needs to evict from the cache. So the next time we access this, it will be loaded from the DRAM again. What we also could do is to use non-temporal accesses, which do not get stored in the cache at all. Or, what we have seen, we can also use uncached memory, as Van der Wien showed us on the Android system, where they had bit flips on mobile devices.
Yes, uncached memory sounds really unsafe because we don't need cache eviction then.
So now we can have bit flips, but how do we target accesses, Michael?
Yeah, so we usually don't know anything about the addresses and where they're actually stored in which row of the DRAM. But luckily, in 2016 at Black Hat Europe, Anders Fogh and I presented a side-channel attack drama, which allowed us to really get a good picture of how the data is stored in the DRAM and which address maps to which part of the DRAM and how do we target specific rows in the DRAM for our Rowhammer attack.
Okay, so what you're saying is now we can induce random bit flips, right? Random bit flips. That's what we all heard about Rowhammer. It's random bit flips. And here the question is, if it's random bit flips, can't we use this in some fancy ways? True randomness is really expensive, right? And it turns out this is not true randomness. They are not random. If you hammer the same locations again, you will get the same bit flip pattern. It's highly reproducible. So what you can do is you can think of a data structure that you want to modify and think about the bit position that you want to change. And then you scan the entire memory for bit flips at the right offset and then try to move your data structure there. For instance, by spraying. And then you can trigger the bit flip again, and you have changed exactly the right bit to exactly the right value and can do whatever you want with that.
Yes. In addition, you can also build a path with it, because it's not random.
But you cannot build a random number generator. Okay, so when we have bit flips now, Daniel, what can we do with them? So it's just one simple bit. Any ideas about what to actually exploit with that?
In 2015, Seaborn and Dulian showed that we can modify opcodes, because opcodes have variable length, and you might have a syscall instruction included in a longer opcode. So you have a long opcode, and part of the opcode could be interpreted as a syscall. But usually, because in Chrome NaCl or something, you would have sanitization running, you could not jump to this disaligned memory address. And what you can do now is you can induce a bit flip at the right offset, and then you can jump to this disaligned memory location and perform a syscall. Yeah, they showed that you can exploit the Chrome NaCl sandbox with that. But what do we do if we want to have a more generic exploit? For instance, get access to ring 0. And there we can attack data structures that belong to the kernel. For instance, the page tables. If you think about the page tables, we have here the present bit, the write access, user space access, write through uncached, reference, dirty, the size bit, the global bit, and the non-executable bit.
And we have, in addition, we have some bits that are not even used there.
Yes, and the large red part, does anyone know what this part represents? The page number. It's the page number. And if we flip a bit in there, then the mapping from a virtual address to a physical address changes. Luckily, page tables are organized in 512 such entries in one 4 kilobyte page. So most of the data on this 4 kilobyte page will consist of physical page numbers. So maybe we should learn a bit more about page tables.
Yeah, if we look at the page tables, it's a really fundamental concept of virtual memory nowadays. So in our programs, we have our virtual addresses. We call them usually just addresses because we are never in touch with physical addresses. And they somehow map to some part of the physical memory. The data has to be stored somewhere. And there we have these page table entries and the whole paging structure behind them. And they then actually map this virtual address to one physical address. And the interesting thing is, so they can map, page table entry can map any user page or kernel page. And the cool thing is, if we modify this page table entry, as Daniel said, we can make it map a different physical page. So we could map any page that we have in memory and then access it using this virtual address. So then we could map some kernel pages or other page tables or some other user pages. And this is really nice. So no sane operating system would allow that.
Okay, so what we can do here is we can first scan for the bit flips as we said. At some point we will find a location where we have the right bit flip in this 4 kilobyte page. And then we release this page. We free this page and spray the entire memory, fill the entire memory with page tables, including this memory location. And then we will get to this picture here.
So what happens now if we trigger the same bit flip on the victim page that we had earlier and released? With a high chance, we flip a bit in the page number, which now points directly to one of our page tables that we control. And what can we do with that, Michael? Now we control everything, right?
Now we have write access to a page table. So this is really nice. We can map anything, read anything, write to everything. So we just simply scan for bit flips, exhaust the memory to have a lot of page tables in the memory, and then flip one bit. One page table will point to a different page table. We can rewrite the page table entry, and we have full access, read anything, write anywhere primitive on our computer, which is really nice.
So these were the basics about the Rowhammer attack. This is all 2015 and earlier. But then there were also other attacks. For instance, Yeah, so this first idea was from 2015, and it was also reused later on in other works. We used it in Rowhammer.js. It was also used in 1-bit flips, 1-cloud flops, and then in the DRAM exploit as well.
Okay, so we can flip bits, and the interesting thing is we can't only flip bits in page tables. We have a lot of more possibilities. When we have bit flips, we can modify binary pages, have different code, credential structs. We can corrupt keys or signatures, so basic fault attacks we know. We can modify certificates to point to different stuff or make them valid again. We can flip configuration files, because we usually have some binary configurations in there to enable or disable something. So there are many, many possibilities with just one simple bit flip that we can induce with Rowhammer.
Yeah, and pages are pretty unique. They have 32,768 bits. They are usually not identical by coincidence. And this brings us to the next point, page deduplication. This was exploited in several attacks by VUSEC, and they also scan for bit flips. They find a location where they have a bit flip, and they have another page that they want to relocate there so that they can induce the bit flip on this page. And they do this by storing the same content on this vulnerable page and then waiting for deduplication. The deduplication hopefully will deduplicate in the right direction, and if it does, then we can induce the bit flip on this page that we actually should not be able to write to. Yeah.
So what can we do now? We scan for flips again. Then we place the content that we want to deduplicate so that the bit flip can be exploited in the end. We perform the bit change through our Rowhammer attack and profit.
Yeah, this is also an idea that's from 2016. And also with those bit flips, we can do a lot of interesting stuff by flipping pointers, pointing to different objects, and corrupt keys, make the user install updates from untrusted sources by modifying their update file. So there are also quite interesting ideas. They've already been done before that.
So apparently we have a real problem, because we can just induce bit flips, get root privileges, corrupt something different. Can we mitigate that?
There were, of course, different proposals to mitigate that. So we can distinguish between, we can detect it, we can prevent it. Prevention is usually better than that. We can do all the stuff either in software or in hardware, where software is for us easier. And then we can talk about short-term solution, quick fixes that fixes it for some time, or long-term solutions, which are the really good solutions that we then should apply. So can we talk about some of them?
Yes. So there are also some solutions that maybe do not work. The first that comes in mind when we look at the earlier slides, we just use CL flush to kick something out of the cache.
But yeah,
we just forbid this instruction, right?
We can use Rowhammer.js instead, the eviction approach. There we don't need CL flush, and it works just as well, right?
Or you also said that during the refresh interval, we can trigger the bit flip. So we just increase the refresh rate so that the content gets updated earlier, so you cannot induce a bit flip.
Yeah, but that also does not work. In 2014, Kim et al. Already showed that on some modules they would have to increase the refresh rate by factor 7. And this would significantly reduce the performance of the DRAM module. So this is also not really a good solution. There was a mitigation implemented by most or by many BIOS vendors where they doubled the refresh rate, but this effectively brings little on most platforms.
I would rather have it implemented on hardware level, like use error correcting codes in DRAM, ECC RAM. That should be a lot better because they are designed to prevent exactly that.
That's correct, but there is no standard for event reporting for ECC memory. And that's quite bad because there was in 2016 a study that found that some servers count the ECC errors, and only if they reach a certain threshold, the errors would be reported. For instance, 100 bit flips per hour. Only if it goes beyond that threshold, they would be reported. And in some cases, even the OS was never informed about errors, not even uncorrected errors. And this is quite bad if the system continues running, although it has ECC memory.
So there are also some other solutions that we have in hardware. So the original ideas were proposed in the Kim et al. Paper that showed that we have those bit flips. So an easy approach is we just make better DRAM chips that are not prone to bit flips at all. Or we use ECC like Daniel described now, or we just increase the refresh rate. But all of that is not sufficient. ECC is a good way to go. In addition, we could, after manufacturing, check if there are any cells that are vulnerable to the Rowhammer attack and try to remap them or retire them so that they are not used. Or we can identify hammered rows at runtime and try to refresh them automatically so that you cannot induce any bit flip. But all of those are in hardware. They're either expensive, there's a performance overhead that comes with them, or also we increase the power consumption. And for instance, on mobile devices, we do not want to do that because we want our phones to last longer.
But these are not the only proposals. There were a lot of proposals afterwards of researchers trying to prevent the Rowhammer effect. For example, the PARA, the probabilistic adjacent row activation, where this was also in the original paper still. So every time a row is closed, we open with a certain probability an adjacent row. So if we hammer, then we have a lot of row closings, and we refresh the neighboring rows more often. And that should help us to also refresh them and prevent the Rowhammer effect. This is quite easy to implement in hardware and doesn't have a huge overhead and can give quite good results, I would say.
Okay, but only as long as we can only induce bit flips in adjacent rows, right? If this is not true, then we have a problem. There was also a similar technique. I would say it's a bit similar. It's target row refresh and pseudo-target row refresh. And this pretty much works like this. You hammer 2 memory locations, 2 different rows, and you have a counter per row now. And this is just incremented as you access memory locations. And if the counter reaches a certain threshold, the corresponding row is refreshed. So you can see it here. Now it's refreshed.
Yeah, it sounds okay if you have bit flips in the adjacent rows, but what if the bit flips are somewhere else? So we tried that with TRR active on our system, and we got a lot less bit flips because we didn't have bit flips in the adjacent rows anymore. But a few rows apart, we still had bit flips, so that might not be sufficient.
I think the attacker is not allowed to do that.
It's out of the thread model, I guess. But
okay. Let's go for the no-hammer kernel module. That was an idea from the Linux kernel mailing list in 2016. And here the idea was similar as with TRR, but it's purely in software. Quite nice. So basically a refresh rate of 8 milliseconds would prevent Rowhammer on most systems. That's what we heard before. Factor 7 above the current refresh rate is fine. So factor 8 is also fine. And we use performance counters to measure the number of cache misses per 64 millisecond interval. And if this reaches a certain value, namely 1/8 of the maximum, then we wait for a refresh and block any operation. We don't schedule anything on the processor anymore until the 64 milliseconds pass.
So basically halt the whole system.
Yes.
Okay.
That sounds good, right? But the problem is now if we have different accesses here, then we also reach this threshold because the performance counter cannot really distinguish between all the different rows. And then again, we wait for a refresh, although this was not necessary at all.
So have you thought about the performance? Because this sounds pretty stupid to me if you halt the system the entire time.
Yeah.
And in addition, what we've seen lately with GPU ground pawning unit paper, or with the remote Rowhammer attacks, either Rowhammer using RDMA-based network cards, or our Nethammer paper, which uses commodity hardware to induce remote bit flips, we do not care about that at all.
So maybe we don't want to dynamically see the Rowhammer attack and then stop it, but we want to do some binary analysis. There are the exploits. We do the same thing as antivirus programs. We analyze the binary, and if they have suspicious code in there, like the CLFlush instruction, who uses that, or RDDSC or fences, then we can flag that and detect a Rowhammer attack with that.
Yeah. So you asked the attacker to compile the attack with your compiler so that the attacker learns you cannot run this code?
I can also do it in an antivirus program.
Okay, okay.
But I just said you also have those remote attacks, so I don't care about the code on your system at all.
Okay. then maybe then we might want to go back to the performance counters and detect the Rowhammer attack. And if we have a lot of cache misses, then we activate neighbor rows. So similar thing as the stuff in hardware, but in software.
Okay, this was also from 2016. But what if performance counters do not work?
Why would they not work?
Because we run our attack in SGX, and SGX performance counters are not reflected in the normal world performance counters.
But you shouldn't do bad things in SGX.
Yeah, it's also not in the thread
You're
mode.
not allowed to do this, right? Yeah. Okay.
So we come back to some hardware ideas that we have. So what if during boot we scan the entire memory, check those locations where we can induce bit flips, and just block them so that you cannot use them at all?
Yeah, this was proposed in 2017.
Yeah, they also proposed to isolate security domains so the kernel is not next to user space, so we don't have any page tables in our reach for the Rowhammer attack.
Mm-hmm. So this will look like this. So either we disable memory or we leave gaps between the different security domains, right? The problem here is if we use BCAD, there are multiple studies that find that 95% or more of your DRAM might be blocked and unusable. So this is not really practical. A memory overhead of 95%, I don't know. Why do I pay so much for my memory if I can't use 95%? That sounds odd. And also for GCAD, what about pages that are shared between different security domains, shared libraries? Are there no shared libraries anymore? What about non-kernel pages? Because GCAD was mostly about kernel to user space isolation. What about non-kernel pages? So this is all not covered here.
How far do you move them apart anyways?
Yes, because we don't know what the maximum is, the maximum distance between hammering location and bit flip location. We observed cases of more than 8 rows apart, so this is easily above 1 or 2 megabytes.
So it's a similar approach with isolating DMA buffers in physical memory so that we can't hammer with them. But again, we have the same problem, right?
Yeah.
If we move them apart.
How far? Sorry. How far apart should we go then? Then we also looked at performance counters. We did that in 2016. Anders Fogg, together with Herrad, looked at that in 2015. There was also another paper by Matthias Peyer in 2016. And you can observe that there is a Rowhammer attack going on, but it's very difficult to find something which has no false positives. And false positives are really bad if it's about detection of attacks.
But what if you have the case that your performance counters do not get updated at all?
Yes, that's again a problem.
Because you put the attack in an SGX enclave and the performance counters are not updated. So I can hide the attack from your countermeasure.
Yeah.
So far we have seen a lot of countermeasures that were proposed. Some of them exist in real-world applications. Some are more theoretic. And they all use different kinds of techniques to detect, either by analysis, static or dynamic, or in hardware stuff, or software countermeasures to try to prevent or detect. So we have a huge range of all those countermeasures that try to prevent the Rowhammer attack.
So we are safe.
Mm-hmm. Yeah, but they all assume that Rowhammer works the way we thought it works, by hammering 2 or more rows. So what if we have something else?
Yeah, actually, so there are 2 different hammering techniques. We know that there are 2 different hammering techniques. The first is you hammer 1 row and other rows in the same bank, and then you will get bit flips somewhere. The second is you hammer 2 different rows in the same bank.
Yeah, I know that. So I already did that. So I choose 1 row, and then I activate that, and another random row, and again this row, and a random row, and this row. And at some point, I get a bit flip next to the 1 row I activate most often.
Yeah, but we can do much better than that. Because instead of hammering just 1 row, we sandwiched our target row and hammer 2 neighboring rows. And we get bit flips much more reliable and much faster.
Yeah, hammering 2 rows. Okay, we will go for 1 location hammering. There are actually 3 different hammering techniques now. We can hammer only one row next to a victim row. And it works like that. We access one row, we access it again, we access it again, and it works. Great. Bit flips. So we have a demo here. This is one location hammering on a Skylake i7 system, and you can see we are hammering a bit here, and then after a while we are scanning for bit flips, and oh, a lot of bit flips.
It's even with DDR4.
Yeah, that's DDR4. And with TRR, no, that's without TRR.
That's without TRR.
Yeah, that's without TRR.
But we still get a lot of flips just by accessing one single row.
Why does that work?
Yeah, it doesn't make any sense because, as we said, we have the row buffer, which serves as a cache. But in addition, what we have are so-called memory controller policies. Because at some point, the controller needs to decide if it needs to close the row or keep it open. So the open page policy says we keep the row open and buffered.
Yeah. So that means that we will have a low latency for subsequent accesses to the same row and a high latency for accesses to other rows, right? That was the case that we observed in the beginning.
Yes.
Yes.
We also have the close page policy where we just immediately close a row and prepare to open the next row.
Okay, this sounds like it would have a medium latency for accesses to any row, right?
Yes.
And why would we use that?
Yeah, depending on the policy that we use, we can either save memory power consumption or increase the performance of the overall system. So
Yes.
we also have adaptive policies that change depending on the usage patterns in the DRAM.
And particularly on multi-core systems, the performance of closed row policies or adaptive policies is much better.
So where can we find which policy?
We can test that. We can run a side channel attack again and measure which policy is used.
But first, to sum it up, when we have a policy that preemptively closes a row, this would allow one location hammering. And we found closed page policies mainly on desktop computers, and on mobile devices, they seem to use the open page policy most of the time.
So the question then is, how well does one location hammering perform? And it performs worse than double-sided. Of course, double-sided is the best. It performs worse than single-sided, but still, we get a very nice distribution of bit flips across the 4 kilobyte range. This is a 4 kilobyte page split up into lines. Every dot there represents 1 bit offset in the 4 kilobyte page. And the distribution of 0 to 1 flips and 1 to 0 flips, they are illustrated in red and blue. You can see that they are approximately 50-50 in all cases. And in the case of double-sided hammering, after 8 hours, we had 77% of the bit offsets covered, with single-sided a bit more, with one location a bit less, half as many, not a bit less. Okay.
But in the end, with all those countermeasures that we've seen, like with PCAT and GCAT, where we separate the memory, the security domains, we cannot target kernel pages anymore, right? What else can we attack?
We could do opcode flipping. So that's a really cool thing. Many applications that we have running on our computer are performing actions as root anyway. Think, for example, the ping command or the mount command, or explicitly the sudo command. They perform actions as root. And the sudo command asks for a password. But what if we can patch that some way out? So we target the sudo binary and try to flip something in there. And the really nice thing about the x86 instruction is they are so dense. So if we look at the one instruction and we flip bits in this instruction, then in most cases we get a different instruction, not an invalid instruction, but a different instruction. So we have here a
jump equal for the password check?
Yeah, that's a jump equal. So we check the password and then jump equal and we do the stuff.
And then you halt the CPU when you do
Yeah, if I flip there, I halt. It's a privileged instruction. But there are more instructions. I can get an XOR, a push, some prefix for other instructions, jump lower, jump overflow, jump below or equal, or jump not equal. So we can invert the logic. So it's really nice that all the instructions, the jump instructions, are grouped together. So flipping one bit gives you, in many cases, a different jump instruction with a different logic.
But that's not all that we can target. So besides conditional jumps, we can also flip comparisons in general, or operands in the comparisons. We can change which addresses we load or store, or during the address calculation, we can change some constants and then use another address as the value to load. And by manually analyzing one pseudo-binary, we found 29 possible bit flip locations where we could circumvent the password check and run a command as root.
But there are many more to find, right?
Yes.
Yeah, this was manual analysis. Okay, the question now is, if we want to target virtual pages, like binary pages, how do we get them to the right target physical location?
We need a new technique for that. Okay. So it's not that straightforward, because we cannot simply spray our binary over the memory. Binary is only loaded once in memory and then it stays in memory. And this is in some cache, an operating system cache, and page cache. And only if this page cache is full, because we execute other binaries, that it goes away and it's not in the memory anymore. Otherwise, it stays in memory.
Okay. So if a binary is loaded the first time into the page cache, it stays there, and if we evict it, if the page cache is full, it will be loaded to a new location.
But it's
possibly.
Huge, right?
It's huge, yes. We can't just evict the page cache, right? So yes, memory waylaying. So basically, we want to relocate the page and hit it at the right time when it's sitting at the right location. How does it work?
So we have our binary here in green and our target location. And then we can evict the page cache by filling it with other binaries until our binary is gone. Then we reload our binary. It will be at a different location. We can evict it and access the binary until finally at some point our binary is exactly at the location we want it to be, so we can induce our bit flips in the binary.
Okay, but do we really reach all the physical pages?
Yes, don't we get just the same physical page all over again? In fact, we are not, as we can see on this graph. So whenever we get a new physical address for our page, with a high chance it's likely to be a new physical location and not the same as we can see in this plot.
Another advantage of this technique is that we do not exhaust the entire memory. We use pages that are loaded into the page cache, so they can be evicted at any time. So we are not running into any out-of-memory situation as in previous variants of the Rowhammer attack, but our memory usage actually, as reported by the operating system, stays very low, approximately at 65% if starting at 60%. So it stays really, really low, so it's not a problem for system stability.
Yeah, but we can do more. For instance, we can combine Rowhammer with Intel SGX to get a cheap denial of service attack. So Intel SGX is an instruction set extensions which gives us integrity and confidentiality of code and data in an untrusted environment. And it runs with user privileges and is very restricted. So you cannot call any system calls in there. And programs are run in so-called enclaves, which is in a certain part of the memory, which is a protected area of memory called the EPC.
Yes, this EPC is just sitting in the physical memory somewhere, and it's encrypted and integrity checked. And the question then, of course, is what happens if a bit flips in the EPC?
Yeah, so as I said, it's integrity checked. Now we flip a bit, so the integrity check will fail. Makes sense. But it then locks up the memory controller, which means that we cannot do any further memory access. So the system halts immediately and we need to manually reboot it.
Sounds unsafe? It is unsafe. Especially in a cloud environment. Okay, so if a malicious enclave induces a bit flip, the entire machine halts, even in the cloud, which allows us to mount denial of service attacks in the cloud on co-located.
But denial of service is boring. That's not something we want to do. Maybe just put everything together we have already with SGX and the one location hammering and the opcode flipping, and then we build an undetectable exploit. Okay. That would be cool. So for SGX, it's really nice because it protects software from malicious environments. And we can't do anything with this thing that's running in there. We don't have dynamic analysis, we don't have static analysis, we don't have performance counters, so everything is invisible. If we now hammer from inside the SGX enclave, then we defeat all the countermeasures that were proposed. So it protects our exploit from also benign applications.
Great idea, Michael. Great idea. Okay, how does it work?
So this is now a demo for the opcode flipping. And we can see we are on a new Ubuntu system with a current sudo version. If we run sudo, we can see we don't have root privileges here. It asked for password. I have no idea what the password is. So I'm starting the Rowhammer exploit here, and I want to jump this, flip this jump not equal to a jump equal in the sudo binary. We're doing the memory waylaying until we have some offset that we can flip, and this memory waylaying is quite fast. Then we flip the bit there at this target location, and when we now run sudo, it doesn't ask for a password anymore, and we can just run everything as root. And the nice thing is, we can evict the page cache again, and it's replaced by the original binary, and it still works as before, and there are no traces of the attack here. This is a really cool exploit.
What if in the meantime I try to log in with the correct password?
Yeah, I can't log in with the correct password.
Oh, that's unfortunate.
Yeah.
Okay, sorry. So as we see, we have all the defense classes now defeated. We can bypass all of them and can mount a attack, although we have all the defenses installed.
But at least it's a low-key attack, right? So we still need low-key code execution for all of that. So, okay.
Okay. Let's just compare some performance numbers. So for Rowhammer, the reports were that we need at least something like 43,000 hammering attempts, so 43,000 uncached memory accesses within 64 milliseconds. That's around just below 700,000 accesses per second. While handling network packets, we actually access memory locations up to 6 times, the same memory location up to 6 times, depending on the specific kernel that is used. So that means if we can handle something like 111,000 packets per second, we could theoretically do something there, right? But network packets have at least 64 bytes, so we need something like 57 megabit per second. That sounds really unrealistic. Who has a 57 megabits per second connection somewhere?
No, especially not in Austria.
No, not in Austria.
But of course, we have modern and pretty fast networks, so this is not an issue at all.
Outside of Austria.
Outside of Austria, of course. So with Nethammer, we see that we can just send many, many packets to the system and induce bit flips. And in the end, network stacks on ARM, for instance, often use uncached memory, which is perfect for hammering, as we've seen. Or Intel recommends the cache allocation technology for quality of service in cloud environments, where you can allocate the cache to different tenants. So you restrict the size of the cache, and under heavy workload, the virtual machine has only, for instance, 1 cache away, so you can evict pretty nicely using this technology.
But also any other software that is used on your system, any software that uses CLFlush somewhere or non-temporal stores, right? And uses this while handling network requests. Any of this code could be used for a remote Rowhammer attack.
So it must not be the driver itself, but any other application that uses the packet that has been sent. So how can we exploit that?
We can, of course, do the denial of service with SGX again.
Yeah, we can also do denial of service by flipping a bit in the file system. Happens quite often if we run a Nethammer attack, unfortunately.
Or we flip something in a DNS server and do a bit squatting attack.
Or in an OCSP server and make our invalid certificates great again and making them valid again.
Okay, we can also attack crypto. For instance, if we flip a bit in a private key, we can generate a public key for that private key because it can be factorized.
And you can use this with different services, like with GitHub or GitLab, where you upload your public key, then we do a bit flip there, calculate a new private key, and then we can just push our malicious code in your repository.
Yeah, we implemented several of these attacks and found that we can do them in practice.
And as a bonus, we can again evict the page cache and get rid of the broken key, and no one sees any traces anymore. So
that's quite unfortunate. So you say there is a commit, and I can't prove that it's not from me.
It was my commit, and no one will ever know.
Okay,
that's why you should sign your commits, maybe.
Yeah. So we have seen that many academic countermeasures were proposed so far to mitigate Rowhammer.
But we've also seen that we can circumvent all of them.
Yeah, we cannot design countermeasures in an effective way without completely understanding the attack first. So we had these wrong assumptions about this. We need 2 locations to hammer, and then we showed that's not the case. So as soon as we understand the complete attack, then we might be able to design good countermeasures.
Yes, because otherwise we just batch a concrete exploit, but do not solve the problem entirely.
Also something we want to talk about, Apple had a really, really good idea for the iPhones.
Yeah, they wanted to lower the refresh rate to save energy. But yeah, they get some more flips. But they just added ECC memory to their iPhone, so then they had fewer bit flips again.
So they save battery.
Nice trade-off.
Okay, that's a great idea. But this also shows that it's an optimization problem. Vendors will always push towards the boundary where they can push, where they know there it is still safe under the current assumptions, right? But if it was too aggressive, you will have bit flips in some cases. If it was too cautious, you will have a waste of energy. You will have a lower battery runtime. So it's an optimization problem. And also, what if the too aggressive changes over time because someone figures out a new technique? What if the attackers become slightly better over time? It's difficult to optimize with an adversary that works against you.
So what do we learn from that? We have to invest much more into researching attacks because there are still aspects of Rowhammer that we do not fully understand. However, this is really required to design countermeasures that fully protect us against bit flips in the long run.
We also have to keep in mind if we add new features to our CPUs, then there might be new attack vectors, for example with SGX, that we haven't thought of.
Mm-hmm. Okay. And what can we say about what we learned here?
Yeah, so in the end, we underestimated side channel or microarchitectural attacks for a long, long time.
Yes. And the industry and also the customers had other priorities for a long time. They wanted performance and not mainly security. You want performance first, right? But maybe we don't want performance without security nowadays.
Yeah, and we have to always think, is a reliability issue only a reliability issue, or can it become a security impact at some point?
So we need more research to fully understand the attacks and to ultimately mitigate them.
With that, we would like to thank you for your attention.
So if there are any questions?
Yeah. If there are any questions, you can ask them right away at one of the microphones.
No questions.
So, in your presentation, you had some DDR4 and 3s that were vulnerable. I think it was like 80% for DDR3 and 60% or so for DDR4. What makes a DDR DIMM vulnerable and what makes it not vulnerable?
In general, the statement about the DIMM module being vulnerable is it's an empiric one. It's someone tried and was able to find a bit flip, so they said it is vulnerable. But if you don't find any bit flip, that does not mean that it's not vulnerable. It seems that there are differences in the manufacturing process. Even modules that are almost identical, that have the same serial number, might have a very different profile in terms of bit flips and susceptibility to the Rowhammer attack.
And all of those studies that did not use many modules. Yeah. So in the end, we need a study with many, many, many modules to really say that this percentage is vulnerable.
So you cannot say that one is cheaper and it has more bit flips, the other one is more expensive.
We were actually hoping for that, so we bought several cheap DDR4 modules, and no, we didn't find an obvious correlation there.
Or one is 4 gigabytes, so it's less dense than a 16 gigabyte.
So we haven't found anything in this direction yet. Okay. So I guess it's more about in the manufacturing process, where exactly, if you have this die where the chips are from, at which position this is and what influences it had during the manufacturing process.
Mm-hmm. And in your experiments, you said that the system didn't have the targeted row refresh mitigation, right?
So we had one system with this one active, and we still had some bit flips there, but a lot less. And on the other systems, on most systems, it's not available. It was just on one server system.
And not in the rows next to the target row, but
yes,
more rows.
We had 0 bit flips in the adjacent rows, so their TRR works as designed, but it doesn't prevent Rowhammer attacks. Basically, that's the takeaway here.